Yes, I wanted to make a comment before starting. Usually, I mean, one does not really need the first session to attend the second one, and because I recall some statements, I mean, should be a standalone. Well, that's one thing. And another thing is that I made a slight change in that in the notation, the use of the letters, and I thought that hopefully you won't remember what every letters meant on Monday, so that you will forgive me. And so let's start. Let's start. And so I want to start with some, I mean, not a complete presentation of the background, but a few results which are known in the literature and were influential on the work we did. So we start with Clauser's theorem, which is a theorem on the generating series of Bell numbers, and I think here everybody knows them. Anyhow, they can be defined by an identity with a closed exponential form. And well, I wrote the beginning of the series just. Well, it's a little bit anecdotic, I agree. But anyhow, the important thing is that this generating series, the ordinary generating series without the n factorial, satisfies a functional equation which has this shape. And Clauser used it to prove that the generating series, yes, which I wrote there, so we have t equal some the ordinary generating series function, okay, is not only transcendental on rational functions, differentially transcendental on rational functions, it's differentially transcendental on a field of a homomorphic function next to zero, okay? And that's quite a strong statement, and somehow can raise some curiosity. And I'd say that my outsider feeling on combinatorics is that it's somehow an archetypal example for many reasons. One of the reasons is that this series is associated with an exponential generating function. Let's see if I can do it. Up. Which is defined here like that. Okay, so is it visible? Yes. So it's defined by a closed exponential form. This is quite frequent, and I will show you a large list of examples in maybe 10 minutes. That's one thing. The other thing is that you can get a functional equation, which is not always exploited in the literature, but it's quite frequent also. And the last thing is that you get something which is differentially transcendental. And there is I need to close it. There's something more. If you look at this, at the functional equation, and you consider the homogeneous functional equation, so you just forget the one, the plus one. Well, the solution is associated with the gamma function, and the gamma function, as you know, is hypertranscendental, is differentially transcendental. So there's something, I mean, it's not enough to conclude that differential transcendency, but the whole space of solution of this functional equation here, it's an affine space, as you can imagine, so it's given by B plus, I'm going to say write something that doesn't make really sense, constant time gamma 1 over t minus 1, okay? And this we know that it's differentially transcendental. Well, you already have a piece here. It lets us say that if you have a differentially algebraic extension, you will have only one of it, okay? And this recall also one thing that I hear frequently among you people, that you have a functional equation, and when you're generating function, you're generating series is always the only power series solution. So there's this recurrent in the example. So for all these reasons, I think that this is kind of an archetypal example. And the reason why I say that this does not really make sense. So you know the gamma to the power minus 1 is analytic, but you have put it at infinity. So you have something which is analytic in C star plus infinity. And then actually you have a divergent series at 0. So it's really not really meaningful what I wrote. So anyway, this is an important example which was our starting point for our work. And I would like to cite another theorem in the literature which was motivating. So suppose that you have a solution of a functional equation with rational coefficients, and tau is an operator, one of the following operators. So either the one considered in the quasar functional equation, or the Q difference operator, or the Mahler operator, okay? Then F it's either rational or differentially transcendental over the rationals. So this is actually the theorem you will find if you look at the paper of Adam Chesky, De Frus Ardua. It's a little bit a particular form, but I mean, it includes all the meaningful, it covers almost all the theorem, but it simplifies a lot the statement. That's why I consider a slightly weaker statement than the one it is in the paper, just for having an easier statement to present. So this also is a very strong result, and it's proved using Galois theory, and it's proved by induction on n on the order of the functional equation. And so whatever you're going to see, or whatever you have already seen in the previous lecture, is actually the first step of the induction in the proof. Okay, so just to be clear. And then there's a conjecture, which is also which raises a lot of questions. So there's a conjecture by Pak Yelusidov. I apologize with all the ones who, for my accent, it's very difficult for me. And so it says that if you have a series and then you consider the same series where all the coefficients are divided by n factorial, so what's called the Borel transform of the series, and if they are both the algebraic, so if they are solution of an algebraic function, the differential equation, it turns out to be both definite, okay? And so that there are people who believe to this conjecture, other doesn't. Someone has also claimed to have a counterexample we have never seen, but so discussion is open. But still, even if you, maybe it's not true in this kind of generality, but it's actually true for large part of, of series with maybe extra assumption, and it's one of the point of what will follow, I hope, makes. And a small remark that being both defined means that both series of coefficients satisfies a linear recurrence. They are recursive, as to use terminology closer to the point. So much for the introduction. And so there are many generating series that comes from combinatorics in a weak way. I'm saying, I mean, that's not enumerative problems all the time, but still that are very famous series which satisfies equations and theorem à la Clauser. So I would start saying words on the Borel transform, which is defined in the next line. So the Borel transform is just this operator here. You see it? Yes. Which divides consists in dividing by n factorials the coefficient of the series. And then there's a small transformation phi, which intertwines with the Borel transform in a nice way. So they commute. If you have two series, phi of f is equal to g, if only if the Borel transforms are obtained by multiplying by an exponential. That's one thing. And then the Borel transforms works quite well compared with the derivations, right? So equipped with these two relations, one can, well, prove this statement. And so if you have a series which is solution of an exponential, a functional equation, whose Borel transform is solution of a differential equation, whose coefficients are a little bit particular. They are polynomial in the exponential with constant coefficients. Okay, that's the point of all this. So the AI are polynomials, and you evaluate them in the exponential. So it's a linear combination of powers of the exponential. And then using, well, so, I mean, one can believe it, I suppose, at the glance, using this relation in the gray box. Well, you can actually transform this functional equation in a functional equation like the Clauser one, and actually you can do it from the Bell numbers. If you start with the exponential closed form for the Borel transforms of the Bell number series, then it just transformed by substitution in this differential equation, and then by substitution, I mean the exponential of t minus 1 is the solution of this easy differential equation, and then you substitute, you do things without actually thinking too much, and you get the functional equation that was at the blackboard just a few minutes ago. And then there are a full set of examples which works exactly like that. So maybe it's not, I'm not going to read all of them, but you may find your favorite series on the left. So in the second column, there's the exponential definition of the Borel transform associated, so the exponential generated function. And then the last two columns are just the coefficients of the equation. So there are quite a lot of them. And well, what's next? Yes, the theorem. And one can prove in all generality this results, which generalizes Clauser's statement and proof that there's a general pattern there. So if you have two rational functions and a different than 0, which is not important, that a is equal to 0 is kind of a trivial statement. And if you have a power series, which is solution of a functional equation like one we have seen before, then it's always differentially transcendental as soon as it's not rational. So you have either rational, either differentially transcendental over a field which I define here. So this is a fancy way to say an easy things. Those are meromorphic functions. In an open set containing 0, but you just don't specify the set because you always need a finite number of them, so there will be always an open set where you can define it, and you don't want to be more specific on the domain of definition. The proof relies on difference Galois theory, and so, well, the standard reference nowadays for difference Galois theory is Van der Put-Singer, which is a lecture notes from '97, and but the first work on the topic is back to Frank in 1963, and so there's been a long time with no application, no interest whatsoever, and then in 25 years things have exploded. So that's one thing, and well, I just want to come back on one of the examples I showed on Monday, because the theorem applies also to this to walks in the quarter plane. I just picked one of the models I showed on Monday. So the one associated, you have your lattice with a integer point, in positive integer point. So you start and you're allowed to go up there. No, sorry. Like that, or like that, and you keep going discretely. And did I say something wrong?
It's not the same rules that you have on your slide.
That's what I designed. What I designed on the blackboard is the right one. Okay, sorry about that. Yes, the second arrow should go up. I'm sorry. And so you count this. You count the number of walks that go from zero to ij in n steps. This gives you a power series with with 3 indeterminates with them. So it satisfies a functional equation which has this shape, and you can. This polynomial k allows 2 or many, but these 2 in particular, rational parameterization, which are relied by transformation. So we have seen that generically for v different than 1, the generating series or part of the generating series satisfy this functional equation, and one can deduce that it's differentially transcendental over the rational. What happens for v equal 1? Well, now the polynomial k becomes this with one half the coefficient, and it factors. So you have your parameterization for free. And when you plug the parameterization into the initial functional equation, you get these things here, where tau is not exactly what is not exactly the same operator than in class A, but of course, if you set t equal I x, things are going to be all right, and I square is equal to -1. And so in this case, what happens to this generating function of the walks is that it becomes really, really differentially transcendental over the meromorphic function, which is a little bit surprising on one side and and not surprising in another way. Because if you generically, if you see here, you have an operator with two fixed points. S go in v squared times s. You have two fixed points. What happens here is that the two fixed points collide, and experience says that when you have two nice points that collide, the result is frequently way more complicated. When you have two regular singularities in a differential equation that collides, you get an essential singularities, and irregular singularities, and things are more complicated. So it surprises, it's not. And one can give an explicit form for this series. And we don't have an explicit form nice like that for all the models, but a few of them, part of them. And so you see the Bernoulli numbers, which are called B, like the Bell numbers. So apologize for that. And if you have a good memory of the images and what you've seen, the Bernoulli numbers appeared in the huge table that I showed before. The Bernoulli whatever Bernoulli polynomials, not numbers, but you recover the numbers putting x equal to 1 in the, well, I can show it just for the control. And okay, they are here, so you just put x equal to 0 and you get the Bernoulli numbers, the exponential generative function of Bernoulli. And we were here. Okay, so other examples that are linked, and we have seen some particular cases. We can say something more general. We have seen particular equations on Monday. These are iterative functional equations. And so the result, the general theorem is the following. If you have a rational function which is 0 and 0, the first coefficient is either 0, 1 over roots of unity, and you suppose that no iteration, I mean composing R with itself as many times as you want, gives you the identity, then you can get a quite similar statement. It means that if you have a functional equation f of r of t is equal to a of t, f of t plus b of t, where a and b are rational function and f is a Laurent series, then either f is d transcendental over c of t, or that's a little bit more complicated. If b is equal to 0, f is algebraic, and it's even the root of a rational function, cannot be many things. If a is equal to 1, then f is rational. And if we are not in the previous cases, f is solution of an order 1 linear differential equation. And this, I think, deserves a few comments. Well, the functional equation actually comes from the first point. It means that if you have a f of r of t is equal to v of t, f of t plus b of t, okay, and then you have a solution of the associated, suppose you have it, don't, of the associated homogeneous equation. Well, if z of n belongs to c of t, well, then you will get some n z prime over z belonging to c of t. And actually, this is going to be the coefficient alpha that appears in the functional equation. So it actually comes from the homogeneous associated equations in the calculation. And one more thing that I wanted to comment, there's a paper by Schäfke and Singer. I guess it's 2019, if I remember correctly. Yes, I think 2019 or 18 maybe. I mismatched the preprint with the published form, but it's around there. And they are interested in systems which have this shape. Either you have a functional equation, not differential, with matrix A, let's say GL C of t. And then you have a differential equation where B is just a square matrix. And you suppose that these things are compatible, actually, that you have a common solution. Compatible means that when you consider the commutative relation between tau and the derivatives, this forces a relation and an equation on the coefficient, and you suppose that two matrices actually satisfy this relation. Okay, so it's an integrability condition, and they consider, well, different cases actually for tau of t is equal to t plus 1, but the usual suspects. Okay, and they show that if you have a common solution, it's actually very simple, rational, algebraic. You cannot find complicated things, but to do so, and even if you can reduce the system, even when in total generality, you can reduce the system to matrices which are very simple, they're constant things, but it proves several results. And the problem to apply it here, because it would be the case, now you see F satisfies a system which is very similar. The problem is that they use a lot of analysis in this, and they use a fine analysis of singularities, which we don't actually have in such a complete way for this kind of iterative functional equations. In this setting here, singularities which are regular, singular, irregular, they're well understood. You have quite the technical arms to attack the problem, which we don't have here yet. So just to comment the statement, and well, I start with an application which is maybe not the most striking. So if you consider permutation, sigma n is the symmetric group of order n, which avoid this consecutive pattern 1, 40, 2, 3, which is the definition is right below. Means just that you cannot have this inequality in the permutation, sorry. And one consider the exponential generating function of this thing. So every coefficient counts the permutation with this property of in sigma n. Then this thing has been studied, and not really the exponential generating function, but something close to is the ordinary generating function associated to the S hat in there, satisfies a functional equation like that. And it has been proved by Beaton, Conway, and Goodman that this thing, S is not definite, okay? So S is particularly the transcendental of a C of t. And there's also a question, would the previous theorem simplify the proof of the not definiteness, since we only need to check order 1 differential equation, not all generality, maybe things gets a little bit easier. Well, we don't know for now. And yes, I show you again, just need to exclude order 1 differential equation. So that's one thing. And then the theorem applies to other example I've already shown, just considering the complete 2 of 3 trees, which means I put an H more. There's no H here. So complete trees are trees that start with a vertex. They go down. The distance of all the black dots from the upper vertex is the same everywhere, and the size of these things is the number of black dots of leaves, and this gives you a generating function, and this generating function satisfies this functional equation, and where the fact that you have the exponent 2 and 3 is not accidental. If you consider more general trees, you will, if you allow us to have more branches that comes out of a vertex, you will find the right pattern there. And this T of T is the transcendental of a C of T. And it turns out that you don't need sophisticated results to eliminate rational solution, just because, well, the R is a polynomial, so you see that if T is a rational, then you cannot have denominators, and then you look at the degrees and you see that, well, nothing is possible. So actually, and the other example that I already showed is the one of the Sierpinski graph, and when you iterate, at infinity this construction there, you get a fractal structure, and you can consider excursion going from 0 to 0 on this fractal structure, and the green function satisfies this functional equation. It has been already considered by Graber and Vos, who proves an asymptotic for G that exclude the algebraicity, and so you automatically get the transcendence, and in particular not the finiteness. Okay, so that's one thing. So so these results are proved with Galois theory, and well, I've tried to play around with a naive approach of Galois theory, which is not always possible for the reason that as soon as you're normally given one solution of your functional equation, and you need all of them. And as you have seen with gamma to the power minus 1, it's not always easy to find a natural space of function where to find the solution, and you don't want to find this solution. So you have to do things a little bit in an abstract way. Sometimes we are compelled to do things in an abstract way. So I hope I convinced you it's worth trying. And so if you do things in an abstract way, so you have a field of characteristic 0, it's important. Although, one forget about this after 3 minutes. And an automorphism, which is not periodic, and so on and so forth. And then you have your field of constants, are the element of the field that are fixed by your automorphism. And we suppose that it's algebraically closed, just to avoid any problem. Otherwise, one has to do things even in a more abstract way. It's not very serious, but so the example typically you can take K to be the power series, the Laurent series, and the operator which appeared in Clausius equations, and then that's our example. And you consider a linear equation which is written in matrix form, okay, and where y is the vector of unknowns, and tau acts component-wise anything, matrices, vectors, and so on and so forth. So that's the starting point of the theory. And then you want to find a ring where you can do things. And so a ring which, whose definition may be a little bit technical. So a ring which has an action of tau, okay, I'll start with my field K, and I find a ring here, R. We have tau, and I want to extend tau up there, and then I want that this ring is tau simple, so it's something also a little bit so it means that R does not have ideals, proper ideals, invariant by tau. So it means that if you have an ideals which is transforming itself by the operator, is either 0 or the whole ring. And this ring contains an invertible matrix of solution of your first of your equation. It means that it has n columns of solution which are linearly independent. So how do you construct this ring? Well, it's more. It's a lot of, I mean, you find this definition, of course, in all the books, but the construction, the idea of the construction is it's easy, then checking things is maybe laborious, but the idea of the construction is easy. You start with rings of polynomials, so X, it's a set of indeterminates, X, E, J from I, J from 1 to n, and it's just a ring of polynomials, and you just extend tau, setting the tau of x is equal to a of x. And so here you have a ring where you have a solution. It's a little bit too large, maybe. So I shouldn't have written this here, but here. So you have a ring where you can find a solution. It's not really satisfactory. I mean, for nobody, I don't think I need to explain why. So you divide by an ideal that minimizes a little bit all the things. And so you consider the quotient by an ideal P, which is tau invariant. So tau P is included in P. This is because you want to preserve the action of tau to the quotient. So that's, and it is maximal among those ideal. Or you go up on a chain and you get to the top. This is possible. Well, that's your ring R. Okay, so it's nothing really scary. And well,
if I take just an example, just try to instantiate it somehow. If for instance tau is time derivation, P would be the radical differential ideal.
Sorry.
P would be.
See, if tau it's a derivation, P is actually a prime ideal, which is not always true, and it would be a radical ideal.
Radical differential.
It's on the top of the things.
Okay. Merci.
Well, differential algebra is somewhat easier than difference algebra. In differential algebra, if you take tau to be a derivative distance, is always a prime. So your quotient is a domain with operators. It's not the case most of the time, actually. So this Picabassi ring always exists. It's easy to describe. And a stupid example, baby example, not stupid. Baby example, if you have an equation which is an order 1 equation tau of z is equal to a of z, but, well, you add the entries of a matrix of solution z, and you add the inverse of its determinant, and that z to the minus 1. So you have your things. That's what you like. So with this ring, you can define actually a Galois group, okay? So the Galois group is the ring of automorphism of R, which commute to tau, and gives the identity of, on the base field. So it's totally parallel to the situation of the classical Galois theory that maybe you know. And, well, the thing is that since it's fixed K, it must transform solution into solution. So that's what is written here. If you take an automorphism of the Galois group, small phi, then it must transform a matrix of solution in a matrix of solution, and which is written here. I think I've done this calculation 2 or 3 times already. It's just because you get an A minus 1A in the middle and erased. Okay, so the inverse of y times phi of y, there it's left invariant by tau. Well, I'm going to write it. Just because you get tau phi is equal to y minus 1, a minus 1, phi commutes to tau, and so this is ay, tau leaves a invariant, and you get your phi leaves a invariant, and so you just erase. So this is invariant by the operator, and so it's a constant of the. Did I call it nu? Okay, it's a constant. And this means that you have another morphism.
Lucia, sorry, I think I have a question. So, so my question maybe is, what is Y? I think I understood that the matrix defined by the indeterminate
Y,
X.
yes, it's a matrix of solution.
Yeah. So in your description, it's just the matrix of Aij, right?
Yes, it's the image in the quotient, if you want to be actually precise. Y is the image of X in the quotient here.
Thank you.
It's your solution in one solution in R.
And it's invertible because you have inverted the determinant, right?
Yes. Yes, so that's when you look for your ideal P, you save. Okay, and this gives you a morphism group, which is, well, if you want to say it in an elaborate way, it's a faithful representation, it's injective, it's whatever nice property you want to find, you can imagine it applies here. And then actually one of the fundamental property of the theory which allows you to do things is that this object, the Galois group, is actually something geometrical. And so first of all, as I said, G and G L nu of C, it's an injective group morphism, but one can say more, G and G is a variety. That's something I've already which is itself a subvariety of A u squared plus 1. Okay, so it's defined, I mean, it's an algebraic subvariety, it's a set of zero some polynomials, and as such it has a dimension as a variety, and this dimension is equal to the transcendent degrees of k over r, which means that over r over k, so it's the number of entries, I mean, roughly, really, people in algebra wouldn't like this definition, but it's the number of entries of y which are algebraically independent over k. Okay, so it's actually a theory which gives a lot of information on transcendence of solution, and so, I mean, when a function and its derivative, they are algebraically independent. They are not solution of the differential equation, and that's how differential transcendency show up in the picture. As an example, well, our baby example is always, it's there. So if you start with this order 1 multiplicative equation, well, the Galois group must transform solution into solution. So it just multiply the solution by a constant, cannot do anything else. And so the Galois group is a subgroup of C star, so the constant without 0 and with their multiplications. And it turns out that if Z is transcendental over K, well, the Galois group has dimension 1, it's the whole multiplicative group. And if it's algebraic, well, you must look at the subgroup of C star, which has also subvarieties. There are only a few of them, well, many of them, but not so many. There are only the groups of unity, of roots of unity. And this means that Z himself, it's a root of a function in the base field. So if the base field is a rational function, it will be algebraic, and it will be the root. Pardon, sorry. The root of a rational function. I got some stroke. I like write on the blackboards, but I have a problem with choke. I mean, anyway, I choke with choke. Marnie Mishina explained me that they are pronounced in a totally different way, the choke and the choke, but for me are the same. Deeply linked in my life. Sorry. Anyway, a little bit more. Thank you. Merci. Merci beaucoup. Anyway, this is closer to the example we have seen before, and I think also comment on this quite a few times. To the previous.
To the previous one, yes. Can you do a little bit more slowly how you deduce that z to the n is rational?
Ah, okay. So, oh yes, you are right. I will use a theorem that is in the next slides. Sorry about that. Anyway, the thing is easy. So you have the phi of z is equal to c of phi z. And this thing is in a group of roots of matrices. So this is equal to 1. And this means that phi of z to the power n is equal to z to the power n. And then you use the Galois correspondence. And I was a little bit too eager to show you this example. I should have put it later. Correspondence. okay, which tell you this for all, when it's for all phi in the Gala group is equivalent to say that Z, okay, is rational, okay. I'm going to, good point, thank you. Same things here. You have this, you transform this linear equation into a system, and then the matrix of solution, well, it's not surprising, is built up with the solution of the initial functional equation. And your Gala group, well, it's given by the entries of the matrix of Z and Y times and the inverse of the determinant, so not. And every element in the Gala group, pick a Vizio thing, sorry. The element of the Gala group, well, they must respect all these relations, so you will have a constant here and another constant here. And if you look at them in a matrix, you write them from a matrix point of view, they just act multiplying on the right by this matrix here or constant. And it means that your Gala group is either equal to or included to this, this group of matrices with these two constant here, which have no constraints in general. So what tells you the theorem that I showed before? Well, if the Gala group has dimension 2, then it's equal to all the G tilde group, of the group G tilde, and the two solutions algebraic independent. If it's smaller, then there's an algebraic dependency. If it has dimension 0, they are both algebraic. So this gives you an idea of how things are used. And, well, it's not so important. I don't think people really think about this when they work, but it's good to know, although it can be technical things. So as I said, this ideal P has no reason to be a prime ideal, and it turns out that actually R is a direct sum of domains. And so you can take the total, what is called the total rings of fractions, so you invert whatever you can invert in these things, what makes sense to invert. And you get something which is not a field, but it's a direct sum of field. And you have an action, a transitive action, tau send one of the field into the other. And that's the place where people work in proofs, okay? So it's not so important, but yet if you want to really do something, it becomes important. And this sum, it's called a pseudo, I don't know, field, which is uniquely determined by some property in a list of property. So the first one, it says that you don't have a nilpotent element, and whatever is not a zero divisor is invertible, knowing that zero divisor are just vectors that have zeros in the wrong places. I mean, in a complementary situation. The constant, so you can extend tau to L, and the constants are the same. You have not increased the constants. You have at least a maximal rank matrix of solutions, and L is minimal for the inclusion with respect to the first three properties. So, so it means that any ring with an action of tau which satisfy 1, 2, and 3 contains a copy of your ring R. You are happy when you find something like that, and that's well, you may consider it a technical point, but that's the place where you live in proofs, okay? And now I get to the point that was missed in the proof, as Bruno noticed. So you can take the collection
Lucia, sorry, about the previous slide. Do you really need to pass to the fraction field, the LIs, to have the map tau? Or, I mean, don't you have tau on the RIs already? And is tau finite order on R?
Yes, of course.
Ah, d'accord, okay.
Yes, you have an action of tau on R and even on the RI, and which is already transitive. Yes. But it's actually necessary to formulate properly the second most important theorem of the theory, which is the second property that one uses actually in application. One uses in application. And that's the Galois correspondence. And so the Galois correspondence, you consider the set of all algebra F, which contains K and are contained in L, in this large L, and which has this property here, okay, and which was the point 1 in the previous proposition, okay, if you remember properly, okay. And to any algebra like that, you can associate a subgroup of the Galois group, which is the set of all the automorphism that stabilizes the element of this algebras. On the other side, you can start with all the linear algebraic subgroups of G. G has changed shape in the meantime. Oh, no, it doesn't. No, this must be a G, I mean, a normal G, okay? This G here must be like this one, anyway. And to any of those subgroups, you associate an algebra from the set F, nice F, which is the subalgebra of L, which is stabilized by all the elements of the subgroup H. And that's what you get is the equivalent of the theorem of the fundamental theorem Galois theory, okay, which tells you that these two applications are one the inverse of the other. So if you start with a subgroup, you take the algebra of the fixed element, and then you reconstruct the group using the things. You retake the things that stabilize the algebra, you go back and forward, and it's one of the inverse of the other. Actually, I mean, I'm going to use the French expression, forgive me, the ones who doesn't understand French. This is le nerf de la guerre. I mean, once you have proved this part of the theorem, that it works for K, you are almost done. And it's actually what you use most frequently in application, even in classical Galois theory. It's actually the most important things. So, okay, and so how?
So we are supposed to understand that this tells us why z to the n is in K on the blackboard? Ah.
Thank you.
Can you do it slowly, please?
Well, all the element of the Galois group here, okay, this is, I don't know, you call it mu n sometimes. So the Galois group is the roots of unity of order n. So for any phi, this constant is the root of unit of order n. So you can do this small things for all the phi, and then you deduce that this things is actually in the base field because it's fixed by all the elements of the Galois group. We are using le nerf de la guerre. We are using the yellow thing. So the yellow sentence says that basically whatever is fixed by any element of the Galois group belongs to the base field and vice versa. Okay, so how the transcendence comes into the picture. Now suppose that you not only have an automorphism, you have a derivation. And well, if you go back to the class R example, then well, the situation is just this one. You have this operator which sends t in t over 1 plus t, and it's enough to take t squared d over dt to get a derivation which commutes. And now your pseudo field L is not enough. I mean, you need something where you can also derive, so something much bigger, actually. And it's a result by Michel Wimmer that you can construct this new huge algebra without increasing the constant, without a further assumption, which was not clear at the beginning of the theory. And so there exists an algebra, which is this Carly R, where one has an extension of tau and the derivative, and that the commutation is preserved. That's the tough point. And where you can find a solution of your initial functional equation. So you can derive it, because... And as a differential algebra, this point should miss it. As a differential algebra, R is still generated by y and determinant of y minus 1. It means that it's a smaller one which contains both y, determinant of y minus 1, and all its derivatives, okay? So as a differential algebra, it's a smaller one. And it's tau simple, which I define over there. Okay.
Sorry, by tau simple you mean that's the same definition, so any ideal invariant by tau, or you require that it's also defined?
That's exactly Michel's trick. The very nice things of this proof, because to construct these things, well, you do exactly the same things as here. Okay. Well, I shall erase a little bit. Well, it's actually, I like it a lot. It's fine to like a colleague's proof, no? I like it a lot. So you take a set of n square things, plus n square other variables, which are going to be the derivatives, I'll say delta, and you keep going, delta plus, and determinant of x minus 1. So how do you define tau on this? So you have an infinite set of variables, okay, in this polynomial ring. So you have tau of y is equal to a of y. And you keep going. Tau of delta x, it commutes. It is delta of a of x. Well, you know the Leibniz rule. So tau is defined on delta x like that, and you keep going. So you get an action of tau here, and you mod out by a maximal ideal, maximal among the ideal that are invariants both for the action of tau of delta. It turns out that if you choose this ideal, whatever, it's just an idea which is invariant by tau and delta and so on. But if you choose it carefully, okay, so it means using tough theorems, you can find one which is invariant by delta and tau, and it's maximal among the tau invariants ideal too. And it's very subtle. And proof is not so long, maybe 15 lines, but it's really subtle. And so you get something which is tau simple. And that's what makes this construction work. Otherwise, we should have enlarged the field of constants to something really huge. You don't want to, okay? You don't want to see in your statement such a thing. And so you have this playground, so to say, where you can derive the things. You do whatever you want. Everything works nice. And actually, the idea is that you want to derive your system in this way, so that you have your system, you apply the derivation, there should be an n factorials there, and then the solution is given by that. So when you look for algebraic solution among the entries of the relation, you actually look for differential equation. That's the idea of the things. It can be, I mean, then the formalization is maybe more complicated. So we just, no, almost at the end. So to be sure you can do what you want. You allow yourself, I mean, you consider your solution in an algebra which has almost all the properties up there. It has no nilpotent element, every element which is a zero divisor or an invertible. That was always the line 1 of the proof. It has tau and delta, they commute, and it has the right field of constants. And so you know that these things exist, and you can do what you want into there. And the key general result to prove the previous result, I hope it's what comes next. No, it's not the key. It's the first step of the general results that you need to prove the two theorem I showed in the very beginning. First step is considering, as we have done on Monday, for instance, equation we don't have the coefficient a there. And then for those equations, I'm going to read the statement which I've commented a lot already, on which I've commented a lot already. It's just to remind the statement from the previous lecture. You can characterize a solution which is differentially algebraic in the following way. So either I'm starting from the third one. Either there exists a linear differential operator which applied to the solution gives you something in the base field. So if it's differentially algebraic, the first one, you get a solution of a linear differential equation for free. Or you can reformulate this third condition in a way that does not involve the solution, just involve the coefficient of the equation, and it means that a linear combination of the derivation of the inhomogeneous coefficient has a rational solution. I mean, gives you a tau equation with a rational solution. You know, you can get a linear combination of the derivation of the coefficient of the equation, f, and you consider this functional equation, then you get a rational solution. It's something does not need to be, I mean, you don't need to know the solution. And that's what I tried to prove on Monday. So I think we can keep going. And as an application, let's consider the Bernoulli polynomials. It's the functional, so x is a parameter here, and t is the variable. Tau is the tau we have seen all over and over. Okay, so that's the functional equation. And well, here you can get rid of the term 1 plus t in the middle just with a rational transformation, which means that the homogeneous equation has a rational transformation, and then you keep going. This is differentially transcendental of a c of t, just applying the previous theorem, and you can prove it by contradiction just to see how things work. And the idea is that I'm not going to detail the proof, but it's quite easy. There exist n and alpha 0, alpha n constant, not all 0, and g rational, such that this linear combination is equal to tau g minus g. It was the second condition on the blackboards, yeah, maybe 1 minute ago. The derivative is t squared d of the dt, and the term b is the inhomogeneous term of the functional equation, so is, yes, this one, sorry, this one. And what happens? Well, when you apply the, well, that should be a b. It's my collaborator faults. Some like to call it F, other likes to go with B. I got caught in the middle. When you derive this B, well, it doesn't move the poles, okay? So you only have one poles on the left-hand side. So if x is different than 1, the pole is 1 over x minus 1. Otherwise, if x is equal to 1, one gets a polynomial. But anyway, I managed to see that this functional equation cannot have a rational solution g. And to conclude the differential transcendence, it's a few lines. If you want to skip lunch and try to do it. And I mean, you wouldn't even skip the entries. So the general statement goes like that, right on time. So consider that you have two coefficients a and b in the base field, and you have this functional equation there, tau y is equal to y plus b. Well, let's skip the situation that we have already considered. So suppose that you have a solution of this functional equation in some field extension. So maybe k it's the rational function, and your field extension are the Laurent series typically. Okay. Now, to know something, you need to find a solution of the homogeneous functional equation associated. You will never find that in the Laurent series, I mean, unless you are extremely lucky. And so you are going just to look for a solution of the homogeneous functional equation somewhere, and you don't care whether these two things make sense together. You just don't care. But you can conclude that if Z is differentially transcendental of K, then W is differentially transcendental of K. Okay? And how do you use that? I mean, I'm not giving the proof, just the idea of how you work out, because of course then you want something more specific for your operator tau. So when you get there, and then you have to work with your specific operator to prove actually a criterion which is user friendly. So take your, suppose, you have tau z, it's equal to a of z, and well, the easy thing is when z is rational, okay, you just make what we call a change. You have that tau w over z is equal to w over z plus b a z, and this thing is in c of t. So you are in the previous situation. That's not serious things. If z is D transcendental, then you conclude whatever is your tau, that W is the transcendental, and then you have to work you have to do something in your specific situation, and that's when Z is the algebraic. So most of the time you don't have much of the algebraic. Okay. How to use the theorem above?
No, but already the first line, if Z is rational,
Right.
so what happened with A?
You have that A, W.
I see. Sorry, I see.
Okay, and you get
Right, I
rid
see.
of
Yeah, I
this,
just
okay?
need lunch. That's okay.
So if Z is differentially transcendental, then you have this general theorem, and you don't really care what tau is. But then, if your Z is the algebraic, well, then you have to work in your specific situation. So the proofs of the two theorems, I don't know if you remember them, we showed in the beginning, I actually have to deal with these things. So hopefully, if you're lucky, there are not many the algebraic solution of a rank 1 homogeneous equation, but that's the idea. So if you just, in this situation, just to have a feeling, so suppose that it's T1 plus T, A, Z of T, and Z is the algebraic. Well, what happens is that there exists what you prove. So there exists a rational function which I can call, goes down, what can I call it? Z tilde of T, such that A is equal to a constant, and Z, let me put it on the right side. So your starting Z is equal to a rational function, Z of T times the exponential, that's the constant C is a constant, an exponential of log, you have to choose a branch of the log, over T. So if you're lucky, you finally manage to show that your algebraic solutions are not so complicated, and then you manipulate them, and you get a statement which is user-friendly to apply. You say, well, you don't need to ask yourself a question anymore. But that's the point where where one starts to work to prove a specific theorem for a specific operator. And 12:30, thanks.
Thank you very much. Camille.
I have two questions. At the beginning, you had Clazar's result where you had the transcendence over the meromorphic functions.
Yes, right.
And then a lot of the time you were over rational functions. So is it just that you change K as you wish, or is there something more subtle somewhere?
Well, in the general part, K was just a field invariant by the operator, so you can choose a little bit what you want. The trick, which introduced some the things in this. Let me. In the specific, I need to concentrate a second. If you, well, that's the general result. Here, it actually, you don't work, you have a base field, which are the meromorphic function, but your coefficient, your solution are in a smaller field, which is not seen by the Galois group, okay? And so it introduces a little complication in the proofs, and you have to do a little bit of analysis because the Galois group doesn't see it. It's not, I wouldn't say it's difficult, but one has to be careful to check what happens. And well, something important to say maybe is that what you need to prove at the very beginning to start with is that if you have a rational solution of this functional equation, it's a rational is a power series, which is a solution of this. It's actually divergent, which excludes. So it's either divergent or a rational function, and then you can start actually working with Galois theorem. Okay.
And my second question was, you always use this example, t over 1 plus t. How much freedom do we have? So if I want t over 1 minus t, does everything works the same?
Your technical abilities. I mean, you can use any endomorphism you want to use. Well, in the example, I used that because we start with Clauser.
But then where do I have to work? So if I want the same theorem, but with t over 1 minus t, where do I need to put work?
That's with t over 1. Minus, oh no, that's not a serious thing. Sorry, I thought you wanted to put a general endomorphism. No, so if tau of t, let's do a tau and a t which are different. 1 plus t, then tau minus 1 of t is equal to t on 1 t. Okay, so it's not you have exactly the same theorem. Actually, yes, but thank you for your question. So the important thing is that this operator is a Mobius transformation with only one fixed point. So if you have a Mobius transformation with two fixed points, you send this two fixed point at 0 infinity, you get a Q difference equation. And Q difference equation always have meromorphic function, meromorphic solutions. And it's not true. So when you have a Mobius transformation with one fixed point, and you send this fixed point to 0, then you don't have many solutions which are analytic convergent. If you send the fixed point to the infinity and you look the solution next to 0, that's more, well, you have an easy example. It's gamma of t minus 1. It's analytic, and it's gamma t plus 1 minus 1. It's equal to gamma t minus 1 over t. And it's analytic at 0, but it's because you just send the point at infinity. You have a richer or a poorer theory, I don't know. Okay. That's actually, I said that when I showed this theorem, I simplified the proof, the statement that is in the original article. One of the simplification I did is not to consider the operator tau of f of t equal to f of tau plus 1, which is a little bit special and complicates the statement because it's a little bit different of the other, and they have a whole statement for all of them, but actually I prefer to.
Okay, one last question maybe? No, everybody's hungry, so let's thank Lucia again. Thank you very much.